Okay, so I just watched the video on the ultraviolet catastrophe and quick review before we move on of how things are excited. So light is emitted from charged gases as atoms are excited, and this is a model of hydrogen. Hydrogen has a proton, and you can see, and one electron, and that electron, is in one of these energy levels. This is hydrogen in gas form. We'll talk about it being different slightly. So if said electron is here, if it drops down all the way to energy level 1, that's the Lyman series, and that's ultraviolet. However, if it drops from here to energy level 2, we see that it is this blue-green color of 486, almost a cyan color. If it drops from here, this is energy level 4 to 2, it's a violet. 3 to 2, it's this red color that's 656. So we can see these different drops produce different wavelengths of light. Okay. If you drop from 4 to 3, say, you actually get infrared, so non-visible. Still electromagnetic radiation, just not in the visible light. And so this is happening with gases. This is why we see. This is what's happening in the sun. Gases are dropping these different energy levels. And when we put a whole bunch of different gases together, we get basically all of these, the sun being a very high energy thing, lots of energy, is causing atoms to be excited all the time. And when they de-excite, they emit light. Well, different atoms emit different frequencies of light. So when you put it all together, you get white light. Okay. However, a glowing neon sign is only going to emit certain frequencies, and you'll get very distinct colors if you look at it with a prism or a spectroscope or something that's going to separate them. So you'll see spectrum lines, and we'll be looking at some different gases in the lab on Monday. Okay, so it's as these excited electrons drop down, they emit lines of a certain frequency. Because it's very specific frequencies, this is our evidence that these electrons must be in certain energy levels or certain energy states, and they can't exist in the states in between them. So you cannot have an electron at energy level 3.5. Why can't you? We don't have an answer for that, but this is evidence that it apparently can't. It's in one of these energy states. The energy states are not necessarily like a fixed orbit per se, but they are a fixed energy state. And that's the idea of quantum. You can have multiple different quantums or quanta of energy, some multiple of this fixed base unit. And think of that as like multiple of pennies. You cannot have 4.5 cents. That's not actually how money you can in a digital economy, but you can think of it like cents, where yeah, you either have some whole number amount of cents that work. And depending on the energy level, what's dropping from where to where changes the wavelength of electromagnetic radiation released. Some of it can be infrared, it can be ultraviolet, it can be visible, but those change depending on the drops. So it's not just the energy levels don't show us the frequencies of light. So you can have more because there's more combinations of changes in energy levels that exist. Okay, we're going to talk about incandescence, and this is kind of where the ultraviolet catastrophe came in. Incandescence is glowing of hot objects. An incandescent light bulb, a standard old style light bulb, let's get to incandescence, is um, it's the standard old style light bulb. It is glowing metal. So a light bulb was the old type of light bulb you had, this running around the outside. And then this dot in the middle. This dot went to one wire, and you had a resistor. So the thing ran to the outside. So you got a circuit here, resistor. The resistor gets hot, it glows orange, which then excites a gas in the light bulb. The excited gas glows, but the glowing hot light bulb was incandescent. Incandescent will glow in more of a full band frequency. It's not the narrow bands of the spectrum that say this is kind of the visible frequency wavelengths of light. It's not those narrow bands of the spectrum that we got with glowing gases. The reason for that is when solids get hot and glow, the energy levels in solids are not quite as clearly defined because they're squished together. Gases have so much space between them. The solids get more of a smear of frequencies, and the peak frequency, whether that be in the orange range or the blue range, or sometimes they'll call it white hot when it gets really, really bright, is dependent on the temperature of the glowing object. A star being a very, very hot glowing object is definitely white hot. Okay. So because the energy levels are less distinct, you get more of a smear across. So it looked like your frequency spectrum. I'm not going to try to do this in color, but you'll get this. And you'll get a bright spot in the middle, but you'll get kind of fading off on the sides of different frequencies. Okay. That's kind of the basics for incandescence. Peak frequencies are generally measured in Kelvin. A violet star would be nearly twice as hot as a red hot star. Okay, because of violet being the higher frequency. Um, and we've learned in the past that energy of a photon or energy of any light is equal to Planck's constant times the frequency. So energy is proportional to the frequency. The temperature is a measure of essentially of the energy. So the higher the temperature, the higher the frequency of light, and violet being the higher end of frequencies. Um, so we've seen that gases emit a certain frequency of light, and we get these emission spectrums. But there's also something called an absorption spectrum. And what does that mean? It means the energy that the gas will absorb to excite the electrons. And they happen to be exact reverses of the emission spectrum. So if you've got white light and you run it through a gas, say helium, the reason we talk about helium a lot is the sun and many stars have a helium atmosphere. So they're surrounded by non-glowing helium, meaning it's passing through. That non-glowing helium absorbs several of the frequencies of light. So we get actually some black lines, essentially, if you have a really good spectroscope, you would not see them probably with ours, but you get these little distinct black lines where the emission lines for helium would be. Um, there's a few other gases in it, so you get more than just helium. You get the lines for all the gases that are mixed in there because those frequencies of light are being absorbed to excite the electrons in the helium. One of the ways they determine what a star, the distance of a star, or how quickly it's moving away from us, if you remember the Doppler effect was the shifting of waves or the frequency appearing to shift due to motion towards you or away from you. So if the ambulance was moving away from you, the sound appeared to be a lower frequency because the wave was being stretched between when it was emitted. The source was moving. So we've got, you here, got the waves coming out here, but between the waves, that's what the waves are coming out at. But between the wave coming out, the ambulance, yeah, love my drawings, has moved so it appears to be a longer wavelength when it's going away from you. When it's coming towards you, the reverse effect was true, where it appeared to be a shorter wavelength. This happens with all waves, including light. And when things are moving away from us, like stars, it's called red shifted or shifted towards red, lower frequencies. And I believe we talked about the James Webb Telescope actually measures infrared radiation because most of the universe is red shifted away from us. So what visible light is often actually ends up in the infrared spectrum. Or a lot of the visible light does, a lot of those frequencies. So they can look at these, and if the same gases are surrounding the stars, which seems reasonable, that there's only so many elements in the universe, you can look at, and if the lines are the same distance, it's probably the same gases. If those frequencies are shifted down, you can figure out how far they're shifted down and do a little bit of math to figure out that how fast that's moving away from us. There's some math involved in the Doppler effect, and you can just calculate the speed at which the source is moving. So you can do that with stars, and that's how they're calculating that the universe is moving away from us. It's also the shift in these lines is how they tell that the sun is spinning. Depending on which side you're looking at, it's either moving towards us or away from us. So if you're looking at the side spinning towards us, it's coming towards us, and that would give us a blue shift. If you're looking at the opposite side spinning away, it would give us a red shift. Okay, these are called Fraunhofer lines, and they've been very, very important in discovering pieces of the universe and the characteristics of how the universe is moving and expanding. Okay, that is it for today's lesson.